all vectors have two considerations. They have, what were the two again? Direction and magnitude. Very good. Magnitude. And what we're going to do is we're going to do a whole bunch of stuff with vectors. Vectors pretty much open up. I always felt like trigonometry opened algebra up into new possibilities. Vectors do the same thing. We'll use vectors to describe systems. We'll cloud formations. We'll use for population booms. We can look at traffic patterns, all kinds of things using vectors. Just a quick anatomy of a vector. This is the tail down here, and this is the head of the vector. And the magnitude is shown with the body of the vector. So that's the biology of a vector, I guess you'd call it. Column representation and position vector representation, these are biggies. This is, we're not going to spend much time drawing vectors and showing you the sum and difference for drawing. I go right to the representation. These are the coefficients of the x, y, and z directions. So if you look at a Cartesian graph, here's your x, y, and then this is your z going into the board in 3D. And of course, there are other dimensions too, but we won't draw those in our two-dimensional smartboard. But when we talk about these vectors, you're going to see them one of two ways. You're either going to see them with a column vector form or a position vector form. And I'm going to go into position vector form in a little bit. Just real quick with adding, how do you add two vectors? Tail to tail, head to head, head to tail. So it's kind of like I'm starting here. I'm going to start here, and then I'm going to end here with this one, and then I'm going to continue off of that one, and I'm going to come up here. Does that make sense? So that's how we add vectors, head to tail. Now the answer is also a vector, and it's called the resultant, and it goes from, and this is the annoying part, I hope you don't mind, the tail of the first to the head of the last. Can you repeat that with me, please? It goes from the tail of the first to the head of the last. That was way too interesting, but it's okay. You did great. So this is the resultant. The resultant is my answer for vectors, but it's also the mathematical sum as well. So what we can do is we can say for this vector A, and I'm going to move this A over here, B over here. This vector A, we went 1, 2, 3, 4 to the left. So this would be column vector 4, up 1, 2, 3. Okay. For vector B, we went backwards 1, 2, 3, 4, 5. So we would say backwards 5, up 1, 2, 3, 4, 5. So if we're adding A plus B, A plus B, and I'm going to dress these up a little bit. I'm going to put a little half arrow above here and a half arrow here to show that they're vectors themselves. That's the equivalent to doing this 4, 3 plus 5, 5. And what is 4 plus negative 5? Negative 1, and 3 plus 5? 8. So theoretically, this resultant should go back 1 and up 1, 2, 3, 4, 5, 6, 7, 8 to get there. So it works out perfectly. This is what we call vector addition using columns. You can also do it using the position vector forms. But we showed A plus B. Look how easy A minus B is. 4, 3 minus negative 5, 5. So 4 minus negative 5 is the same as 9, and 3 minus 5 is negative 2. Now, what does this mean as far as the vectors go? Well, what it means is that if I took A here and I took the opposite, the arrow actually is reversed. So I'm going to do this by cheating. I'm going to block this out and put the arrow down here. And now when I go for my resultant, the tail starts here, head start from the, where did we start again? From the tail of the first to the head of the last. There you go. And to get there, notice that I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and down what? 1, 2. Perfect. So it works visually, it works mathematically. You can do coefficients of it just as easy as can be. All you'd have to do for 2a is 2 times 4, 3, minus 1/2. Didn't mean to put that parenthesis there. 1/2 times negative 5, 5. So that's going to be equal to 8 plus 5/2, and this will be 3 plus, or 6, yep, thank you, 6 plus 5/2. This is going to be a minus, right, because there's 1. Must be a snow day. All right, so there you get 16 plus 5 is 21/2, and this is going to be 12 minus 5 is 7/2. So there you go. There's your addition and subtraction with multiples. All made easier with that. The magnitude is how long, what the length of the body is. And if you have it in column form or position vector form, all you have to do is take the x, take the square root of x squared plus y squared, Pythagorean theorem, and you'll get the length. But here's the part I want you to circle. Would you circle in your notes this? This means magnitude, not absolute value. Okay? I guess it's a double negative the way I did that, but you know what I mean. And then let's see, what else we got here? Oh, 3D, you just add on another z squared. And so if we want to find the magnitude of this vector in 3 dimensions, negative 2, 3, 1, we'll do negative 2 squared plus 3 squared plus negative 1 squared. And what is that? 4 and 9 is 13, 14. That's how long that vector is. Doing okay? So far, so good? Too good to be true. Now, we're going to do something kind of weird, and it's going to seem really hard at first, but it's really easy in the long run. This little, with a hat on it, is called the unit vector. And all the unit vector is it has the same direction, but the body magnitude equals 1. Now you might say, well, why would you want to do that? Who cares about finding a magnitude of 1? Well, the reason you do that is very similar to, how many of you know the company FedEx? FedEx? And what innovation did they come up with in mailing things throughout the country? What was their big innovation? Do you know what it is? Yeah. Anytime that you want to send a package, they all go to Atlanta. Everything. Anywhere in the country. So if you're like in Nashville, it goes to Atlanta, and then from there, they'll send it out. Now you might say, well, how does that save? Well, think of having all these hubs throughout the country, and all of them have to go everywhere. That's going to be expensive. But what if they all went to one place, and then you take everything and send to one distribution site that goes out to 20, 25 places, and so on and so forth. That was their innovation. And it seems so weird if I want to send a package to Eden Prairie from my house. It goes to, you know, if they built it in Minneapolis, it's going to go to Atlanta and then it's going to go back. They might not do with locals, but and I'm sure they save money not doing that. But more than likely, if you're going to like Sioux Falls, South Dakota, it would go for sure down to Atlanta and then back. So think of the vectors that way too. Let's say I wanted to take my vector 2I plus 3j plus 4 or plus 1k. And I wanted to make this a vector that's 10 units long. Okay? What would be the simplest thing to do with it? Shrink it to 1 and then multiply it by 10. That's what we're doing. We're taking it to Atlanta and then we're sending it to Sioux Falls. That's what we're going to do. So first thing you want to do is find the magnitude of this. How long is this vector? Well, the magnitude of this vector, oh, let's call it vector v. V is for vector. The magnitude of that vector is going to be the square root of 2 squared plus 3 squared plus 1 squared. That's just the square root of 14, isn't it? Okay? We know that this thing is the square root of 14. So what I'm going to do is I'm going to turn it into a unit vector, like this. And so I'm going to take 1 over the square root of 14, and now 2I plus 3j plus k. Now I know that this is how many units long? It's 1. So you want to do that? Wham! Now it's 1 unit long. And what do we do to make it 10 units long? We multiply by 10. Isn't that easy? That's the point of a unit vector. You can make any vector any length you want by shrinking it to 1 and then multiply it by what you want. Now they're showing it this way. Take your vector and dividing by the magnitude, and then you can make it whatever length that you want. Last thing, I want to show you this whole position vector form. This position vector form looks kind of weird to me, but it's going to make total sense, because if we're going from here over to point xy, what happens is that you're going to say that vector v is going to be something, x times something. X times something plus y times something. Okay? X is the distance you go in the x direction, and y is the direction you're going in the y direction. Is that part okay? So how many of these, what we're doing in the x direction is we're taking these little unit vectors I was just talking about, and I'm adding them up. How many of these over 1 up zeros, over 1 up zeros, how many of those am I doing? What does it look like? 5 of them. So, or in this term, x of them. So this is 1, 0. And then to go up, I'm going to go 0, 1, 0, 1, 0, 1, y times. So if you multiply these out, what you're going to get is x0 plus 0y. And if you add across, you're going to get x plus 0 over 0 plus y. So this is how we get what we call the position vector, because this is called little I, and this is called little j vector. And this is your column vector. Isn't that simple? Seems kind of easy. My opinion, love the column vector. Position vector, not so much. All right, so let's, I'm going to have you take this one, and I want you to find the magnitude, the unit vector, make that vector 5 units long and 100 units long. Go. Did you get the square root of 1 squared plus 2 squared plus negative 1 squared? Did you get that? Square root of 6. So the unit vector u is just going to be this 1 over the square root of 6. So if this thing is the square root of 6, we want to divide by the square root of 6. I plus 2j. See how I put the little half arrow above the unit vectors, I, j, and k? I is 1, 0, 0. J is 0, 1, 0. What do you think k is? 0, 0, 1. Yeah. And then you're just multiplying them by those. You don't need these here, but I'm just telling you about them. So then what do we do to u, the unit vector, to make it 5 units long? What do I do to what do I multiply this by? 5, right? And what do we do to make it 100 units long? Simple. Done. And there you go. You've changed that vector. You are ready to do problems day 1. I've got some vectors to add and multiply, a little bit of algebra in there. I think you'll like the simplicity of them, finding lengths. And when you see the word surd, surd means that. Like the square root of 2 is the surd of 2. I don't know. It's kind of fun just to say that word. Rhymes with gird.